Hello class, today we'll be identifying roots by using graphs and by evaluating. So remember that roots are the same thing as x-intercepts, well, kind of, and I'll talk about that in a moment. But think about as roots being where a function crosses the x-axis, okay? Also, remember that a function has as many roots as its degree. And remember, a degree is the highest power of x. So for instance, say if I had y equals x cubed plus 2x squared plus 4, well, this function is guaranteed to have 3 roots because the highest power of x is 3. So we'd say this has 3 roots. However, not all roots are going to be real roots. Sometimes they'll be imaginary or complex roots. And remember, imaginary complex roots are roots that have an I value in them. So that's what I have here in the blue. It says, however, a function may cross the x-axis less times than its degree. So sometimes we'll have like a third-degree polynomial, which will only cross the x-axis once. When this happens, the remainder of the roots are imaginary or complex. So in that case, if we had a cubic function, something to the third degree, and it crosses the x-axis only once, that means that it has 1 real root, but 2 imaginary roots, because we need to hit those 3 roots, since it is cubic. So let's go over some examples here. I have graphed some examples for you, and I gave the function over here as well. And I want to determine what kind of roots are these. I just want to identify how many of them are real and how many of them are imaginary. And that will be the first part of your worksheet today. So here I have the first example on the top left here. I have x cubed plus 4. So I see the cube, which means that there must be 3 roots. That's guaranteed that there are going to be 3 roots. But looking at the graph, when I graph it, it only crosses the x-axis, this horizontal axis, once. Just like my example that I was discussing. So in this case, this has 1 real root, because the real root is where it crosses the x-axis, and 2 imaginary / complex roots. We don't need to identify whether it's imaginary or complex. Remember, complex numbers are just imaginary numbers that also have a real component to them. So let's take a look at the second one. We have x squared minus 6, and this function here is a parabola. It's a quadratic, and we can see that it should have 2 roots, and we see that it in fact does cross the x-axis twice. So in this case, it has 2 real roots. And that means it would have 0 imaginary roots. Looking at this next one, now we have f of x equals x squared plus 3. And when I graph it, we see that the function doesn't cross the x-axis at all. So that means there are no real roots, but there has to be at least, well, not at least, sorry, there has to be exactly 2 imaginary / complex. Over here we have a cubic again. The highest, or the degree is 3, so that's a cubic function. And here we see that it crosses, when I graph it, it crosses the x-axis 3 times. So that means it's going to have 3 real roots. And it doesn't have any imaginary roots. These last 2 examples here are special cases. And this goes back to root multiplicity. So remember that if we have a function that crosses the x-axis, there is 1 root at that point. For instance, right here, it crosses, there's 1 root. However, if it touches the x-axis and bounces back up, that means there are 2 roots at that point. So here, at this point right here where it touches the x-axis, there are 2 roots. Which, this is a quadratic, which means there are 2 roots, which means this is going to have 2 real roots. So, what did I do here? 2 real roots. As if that's legible anyway. Sorry about that. Okay, it's 2 real roots. Yeah. So whenever it bounces, there are 2 roots right at that spot. Here, we have a cubic, and it looks like it crosses here once, and then it bounces here, so that means there's 1 root here and 2 roots there. So that's a total of 3 real roots, which means it's not going to have any imaginary roots, because this will have 3 roots. So all 3 roots in this example are real. So 3 real roots. So that's what I'd like y'all to do on the first half of that assignment that we'll be doing today. We just want to identify, what kind of roots these functions have. Let's shift our attention just a little bit, though. I want to talk about identifying roots by evaluating. So, in this example, well, in this idea here, remember that real roots are the x values when y equals 0, because that's where it crosses the x-axis, and the x-axis is where y equals 0. So, to see if a function has given roots, we want to set y equal to 0 and plug in the root values one at a time. If all resultants, meaning after we simplify, if they're all true, then the roots belong to that function. So basically what I'm saying here is, what if I were to give you a function and I were to say, does it have these roots? Well, what we're going to have to do is, if I plug in, say, -5 every time I see an x and simplify, then and if it equals 0, then that's a root. If I plug in, say, -5 here, and for every time I have an x and I simplify, and equals something other than 0, say 3, then it's not a root. It must equal 0. So let's test these out. Okay, so first I want to see if -5 is a real root of this function. So I'm going to set y equal to 0. Well, I have my function here. I'm going to set y equal to 0, so y is now 0. So 0 equals, and I'm going to plug in -5, sorry, every time I see an x. So -5 cubed plus 3 times -5 squared minus 13 times -5 minus 15. And let me get my calculator. Sorry, I should have had that prepared. Okay. So, my calculator, let's see. I guess we could just plug this all in at once, but you guys don't really have calculators like this. So let's do it separately. So we'll do each term separately. So -5 cubed, -5 cubed is -125 times 3 times 5 squared, or -5 squared. So 3 times -5 squared is 25. Times -13 times -5 is positive 65 minus 15. And then we can multiply these together. I just saved it for an extra step. If you guys can do it all in one step, that's great. So 0 equals -125 plus 75 plus 65 minus 15. And this seems, it's a bit of work, isn't it? but all we're doing is simplifying. We just plugged it in and simplifying. So now we can say negative 125 plus 75 plus 65 minus 15, oh, wrong minus, equals 0. So perfect, 0 equals 0. Negative 5 is a root. So now we need to do that with the other two. We know that negative 5 is a root, but is negative 1 a root? Is 3 a root? So let's go ahead and do this same thing with negative 1. So I'm going to take my function. I'm going to set y equal to 0. So y is now 0. So 0 equals x cubed. It's going to be negative 1 cubed plus 3x squared. So 3 times negative 1 squared minus 13 times negative 1 minus 15. All right, so let's go through this now. I don't think we'll need the calculator this time because powers of 1 are just 1. All we need to do is worry about this the negatives here. So let's see. 0 equals negative 1 cubed is going to be negative 1 times negative 1 times negative 1, which is negative 1. Negative 1 squared is positive 1. Positive 1 times 3 is 3, so I can say plus 3. Negative 13 times negative 1 is positive 13. And we have minus 15. Well, let's see here. Negative 1 plus 3 is 2. 2 plus 13 is 15. 15 minus 15 is 0. So very good. We know that negative 1 is also a 0. But we just have one more thing to do. We need to make sure that 3 is a 0 as well. So again, I'm going to set y equal to 0. And I'm going to plug in 3 every time I see an x. So it's going to be 3 cubed plus 3 times 3 squared minus 13 times 3 minus 15. Okay. So 3 cubed, that's going to be 27. 3 squared is 9. Times 3 again is 27. So we're going to have 27 plus 27. 13 times, or negative 13 times 3 is negative 39. And then minus 15. And let's see here. I guess we could just plug this into the calculator here. 27 plus 27 minus 39 minus 15 equals 0. And there we have it. So, does the function have roots at x equals negative 5, negative 1, and 3? Yes, it does. And I believe on your worksheet it's multiple choice. It asks which of the following functions has roots at each of these values. So my advice to you is to go through each possible answer and start solving for them. Let's do one more example here. So does the function y equals x cubed plus 2x squared minus 6x plus 12 have roots at x equals negative 3, negative 1, and 4? So again, I'm going to set y equal to 0, and I'm going to start with negative 3. I'm going to plug in negative 3 every time I see an x. So 0 equals, let's see here, negative 3 cubed plus 2x squared, but x is now negative 3, minus 6 times negative 3 plus 12. Okay, so negative 3 cubed is going to be negative 27. And then negative 3 squared is going to be 9, but 9 times 2 is 18. Negative 6 times negative 3 is positive 18. And then plus 12. And let's see what this gives us. Negative 27 plus 18 plus 18, plus 18 plus 12, and that is 21. So does 0 equal 21? And in this case, no, it does not. So negative 3 is not a root. we could go over the rest of these. However, we don't need to, because the question is asking, does the function have roots at these three values? Well, I already did the first one, and it doesn't have a root there. So does it have roots at those values? No, it doesn't. It may have a root at -1 and 4, but it would need to satisfy all three of them. Okay? So that's all I have for y'all. Let me know if you have questions, and have a good day.